Good evening. All right. Welcome to the last Voices of Discovery of the semester. Before we begin, I would like to ask everyone to please silence all electronic devices and please stay seated throughout the talk and the brief Q&A session that follows. My name is Diego Hernandez, and I'm a sophomore majoring in biomedical engineering here at Elon. In the fall 2023 semester, 7 students, including me, began working on a knee ankle foot orthosis, also known as a KFO, for a man with a T10 spinal cord injury that had difficulty walking. And although we weren't able to finish it, in these next 2 years, I would like to continue this research under the mentorship of Dr. Hargrove Leak. Building the KFO has increased my desire to make a career in orthotics and prosthetics, a field where Dr. Banks has used his expertise in biomechanics and medical devices to bridge the gap between engineering and medicine. Now, it is my pleasure to introduce Dr. Banks, who earned his bachelor's and master's degrees in biomedical engineering at Case Western Reserve University. He went on to get his PhD in mechanical engineering at MIT. And after getting his PhD, he served as the technical director for the BioMotion Foundation, where he oversaw and directed research related to knee, hip, shoulder, elbow, and ankle biomechanics. Later on in his career, he became a professor in the Department of Mechanical and Aerospace Engineering at the University of Florida. Currently, Dr. Banks is working on 2 startups and a redesign of a common knee replacement. Dr. Banks has received multiple awards and recognitions. These include the Dick Albin Distinguished Paper Award and the Jackie's Jenny Memorial Lecture Honor. He is credited with developing the first quantitative technique for direct measurement of 3D knee replacement motions while patients perform dynamic weight-bearing activities. He is a member of several professional societies, including ASME, the Knee Society, the American Society for Biomechanics, and the Orthopedic Research Society. Dr. Banks served as president and annual conference host for the International Society for Technology and Arthroplasty in 2013 and remains a member of the board of directors. Dr. Banks has been active in orthopedic and joint mechanics research his entire career, and particularly in the movement and function of joints. He also actively collaborates with medical device companies to design and improve joint replacement implants that have been used in over 100,000 patients. In recent years, he has shifted his focus to functional medicine and clinical nutrition. Finally, he's been involved in the field of autonomy and robotics, where his work contributes to developing systems and devices that can operate independently. Now, please join me in welcoming Dr. Scott Banks.
Okay, you can hear me. I can hear me, so we're good. Let me set a timer just so I know what I'm doing, or I'll just put my clock there. It is an absolute joy to be here as a Voices of Discovery speaker. I was last in the classroom last spring, and so I had the pleasure of joining 2 classes today. And I was super excited and highly caffeinated, and hopefully didn't, over-enthuse this, in my presentations. But we had just fabulous interactions, and I really enjoyed meeting and conversing with the students throughout the day, in addition to the dinner that we just had. And so it has just been a delight to be here at Elon, and I just can't say enough nice things with every interaction that I have. My first Elon interaction is a master's student that came to our department. She was on the varsity soccer team here at Elon and wanted to go more into medical device work, and so joined University of Florida, and we worked together as she was a graduate student. That's the first I'd heard of Elon. And then in 2019, my son, who you will know as the director of the hands-on part of the engineering program, said there's this really cool job at Elon, and this is what they're doing. And I was super excited about that, and obviously through that connection have learned about what's going on campus here and just couldn't be more excited about it. So happy to be here. I've got, as you would expect, I have slides. And if I know, so I'm going to be talking about knee replacements because that's kind of my thing. And I've encountered no fewer than 3 people with knee replacements on campus today. The count is currently 2 with total knee replacements, 1 with a partial knee replacement, some going well, some early, some not going so well. So hopefully at least 3 of you will get something out of this. And the rest of you, we'll see. But if you've got a question as I go through, this is a small enough group. Let's just dive in. I'm going to give you a little personal background for context, like why is this guy up here enthusing about knee replacements? For those of you who are not familiar with knees, I'll give you the barest of anatomy. And obviously, if I use terms that you need clarification for, just, what's that mean? And we'll be happy to make sure that that's clear. And then I want to go into sort of the engineering journey of, okay, I got into this field, and I'll explain how, but we needed to be able to observe the system so that we could make it better. And so spent time developing a method, as Diego mentioned, to measure how knee replacements moved after they were in the patients, and we used that and identified the deficits. They weren't working the way that they were supposed to. Took that information and then exercised some of our other engineering skills to design a new knee replacement design, and then have followed that for 2 decades. And so I'll share some of that and then come back to the measurement tool, which is occupying a lot of my time currently. And then for the students here, I'll have a few parting words of advice and context and things, okay? And so what you are going to see is that I'm just an engineer, right? I can't look at the world through a different lens. That's what I do, right? I can't help it. That's where I'm at. So where did I start? I grew up in the western suburbs of Cleveland, Ohio, me and my brother. I'm the short one there. And what's relevant for this is that my dad played college football at Kent State University. He was an offensive guard he was 6'4", like 230. And that was big back in the 1950s. And now that would be a really small tight end, or a big wide receiver or something like that. But because of that football play, he had bad knees. And consistently throughout my youth, my dad was going to get his knees drained, ultimately had a knee replacement and an infected knee replacement and a revision knee replacement and those kinds of things. And so that was really formative in, I think, predisposing my interests to get involved in the medical enterprise. Also contemporaneous with my growing up is I was a drummer. I played in all the school bands. I played in rock bands. I played in sort of punky bands. This was a long time ago. So there's that too if you have questions about it, but otherwise we're just going to focus on knees, okay? Basically the only thing that is noteworthy there is I used to be able to grow hair. And so I then, obviously went to high school. I was good at math and physics and those kinds of things. Again, predisposed towards medical interests, and I took an anatomy class. Oh my God. It just was like, oh, you need to find a way to combine these. And so then I went from the west side of Cleveland to the east side of Cleveland to Case Western Reserve. I went into biomedical engineering because I thought that would be a neat merger of engineering and the medical interests. And this will be a recurring theme. As an undergraduate, I had the good fortune of finding a mentor. This guy, Hunter Peckham, when I joined his lab, I think he was an associate professor. He was young. He was younger than this picture, but Hunter was a guy who was on the path to greatness, really. I mean, he's in the National Academy of Engineering, and you see all these other things. And so I really benefited from kind of being in that environment. And Hunter's passion was developing implantable muscle stimulators for people with spinal cord injuries. And so his focus was high-level spinal cord injuries, so restoring hand function in people with C5, C6 level spinal cord injuries. And the idea is that you would put the implant package somewhere over here around the pectoral area, and you would then tunnel electrode leads into the forearm and the hand, and you could wirelessly power and communicate with that device so that you could actuate the muscles volitionally so that those people could then have hand function that they'd lost through their injury. And so I showed up as, I think it was a sophomore. That is my school ID picture. That's me. And if a kid like that showed up in my doorway, I would have done exactly the same thing. It was like, Scott, we need you to sort this box of resistors by color code. Let's see if he can do that. And I did. And we found that, I dug what that lab was doing, and they tolerated me. And so I ended up doing my senior project and my master's degree with them, developing instrumentation to quantify how these implants worked both in benchtop testing and as well as in animals. So I ran the animal lab where we would put these devices into large dogs and characterize their performance to make sure that before we put them in humans, they were going to meet the needs of that device. And so, super cool. And Case Western Reserve published this probably 10, 15 years ago. I don't know, you might be able to read the date somewhere there. And it was a summary of the 50 biggest things that happened at the university in their history up to that point, including in 1986, a man paralyzed from the neck down is able to grasp and lift a coffee mug for the first time since his 1977 diving accident, thanks to the development of the first implantable electrode stimulator system by Professor Paul Hunter Peckham. And the cool part is that when that got put in, I was in the operating room. So I was the guy that, when they brought in the sterilized implant, and they opened the drapes, and there was wires, and they threw them over to me with a computer, a 1986 version of the computer. Wasn't like this. And basically my job was to go, everything's working, go ahead and put it in. And so that was a formative experience where me operating as an engineer saw that through my efforts, we could do something that was really profoundly impacting for a patient. And that was like intoxicating. And so that's what I kept doing. But I met this girl, Anne, my wife of almost 36 years. She had a fabulous job opportunity in Boston. So I was like, okay, well, I'm following her no matter what. But it was either get a job. That's what my dad wanted me to do. He's like, you got to get a job and support that girl. She didn't need support, but that was that perspective. Or I thought, well, maybe I can get into, one of those Boston schools and pursue a PhD. So I did, and this place let me in, the Massachusetts Institute of Technology. And again, I had the good fortune of running into some really extraordinary individuals. This guy, Bob Mann, ended up being kind of my academic advisor and mentor. And he's gone now, but he is, I think, one of the few people on the planet that has been inducted into the National Academy of Sciences, the National Academy of Engineering, and the National Academy of Medicine. I mean, an unbelievable individual who was very generous with his time and working with the students, and he had an incredible vocabulary. So after we would meet, I would go back to our apartment and look up words that he used. It was great. But he was kind of phasing out his career, so he wasn't hiring graduate students, and I was looking for somebody to pay my freight, right? I couldn't afford all this stuff. And so he sent me over to Massachusetts General Hospital, where a young surgeon, he's not young here, but back then he was, Andy Hodge, he was an engineer by training, but became an orthopedic surgeon. And so he had a teaching appointment in mechanical engineering at MIT, but he was a practicing joint replacement surgeon at Mass General Hospital. And so Andy was basically like looking for a student, and he said, I want to figure out how knee replacements move after I put them in my patients. And my response was, me too. And so he hired me, and this was the context that we began working in, and that is, we're putting these devices in people. We really don't know how they perform mechanically, so we want to learn how they move. This was 1988. At that point in time, in the United States, we were putting in about 180,000 total knee replacements per year. Now it's close to 1 million in the US alone. At that point, they had figured out how to do these surgeries in a way that infection wasn't a huge issue. They could, manage all that, get people out of wheelchairs and restore some quality of life to people that had debilitating arthritis of the knees. But the range of motion, how far you could bend your knee, it wasn't reliably great. Their strength, so stepping up a stair, walking downhill, it was more difficult, and they would fatigue quickly. And the implants, as I'll share with you with some slides, they didn't last that long. And so it's a great engineering opportunity to say, well, let's characterize this system and see if we can make it better. And so that's what we embarked on. So here's our little anatomy lesson. And so what you see on the left there is a arthritic knee. So normally your knee is covered with this amazing material called cartilage that is extremely lubricious and slippery. And so as a bearing material in your joints, you have almost frictionless motion. It's just an unbelievable material. But sometimes the biology and mechanics tip in the wrong way, and you get degenerative diseases that destroy the cartilage, and then you need a knee replacement. And so the basic anatomy, your thigh bone, we call it the femur, and so I'll talk about the femoral component that goes on the end of the femur. The tibia is your shin bone, and I'll talk about the tibial component. Your kneecap is the patella. And then importantly, I'll mention the cruciate ligaments. So anybody in here care to, you know somebody, you've had an ACL injury? Yeah, super common, and I think everybody that raised their hand is female. There's a higher incidence of ACL rupture in women than men. The anatomical shapes in your knees are a little bit different. That gives less room for the ACL. Sorry. But that's not at all uncommon. But the anterior cruciate ligament, what it does is when you extend your knee, that ligament that's basically running in this direction, but it's inside the knee, it becomes tight or recruited, and it keeps the femur from going like that in the knee. It keeps the femur up towards the front of the tibia. When you have an ACL rupture, you sublux this way. So the tibia comes forward or the femur goes back. And we'll talk more about that, but that's not good, right? The other cruciate ligament, it's called the posterior cruciate ligament, and that runs behind the knee, and that one becomes recruited when you bend. And what that does is it helps the femur move to the back of the knee or posteriorly as you flex so that you can clear that space and bend further. It's less common to rupture PCLs. Oftentimes that happens in a car crash where you're sitting like this and you hit the dash, and that happens. So, but that's less common of a sports injury. So we'll talk about the cruciate ligaments, and then on either side, and the inside of your knee is called medial, the outside is called lateral. We have the collateral ligaments, and those are the ones that keep your knee from doing that, okay? And so we'll revisit those terms, and again, if I get into jargon, just say jargon alert, and I'll retrench and make sure that we clarify what I'm talking about. So arthroplasty means replacement. So knee arthroplasty means knee replacement. And what we're going to see in the design of knee replacements is that we're typically resurfacing the end of the thigh bone with a metallic piece. right? And so that is contoured more or less to reproduce the femoral anatomic shapes. And then on the tibia, we typically are cutting off the top of the tibia and putting in a metallic implant as a base plate and putting on top of that a plastic bearing material, and we talked about that at length this morning in the strength of materials class, that gives you sort of the shapes that guide the motions. And so, I got ahead of my slides. So the femoral tibial metallic base plate with a plastic bearing. Your kneecap, it depends on where you live in the medical legal environment. They may resurface it, they may not. Do you know? So our total knee people in here, do you know, did they resurface your kneecap? They may have. It's a little bit controversial. The results seem to be about the same whether you resurface it or not. And so there's no convincing data at this point for most knee replacement patients, whether you do that or not. But importantly for our conversation, in the vast majority of total knee replacements, if the anterior cruciate ligament was there, you remove it so that there's room for that tibial base plate. So the ACL is gone. And then 50% of the knee replacements are designed to retain the posterior cruciate ligament or the PCL. Okay, so that's our anatomic talking. Oh, and the collateral ligaments are always retained for a primary total knee. If you are compromised, your medial collateral ligament especially is not competent, then you'll end up getting a hinge prosthesis where there literally is a hinge mechanism in there. It'll allow you to rotate, but it provides that stability in this direction that otherwise your collateral ligaments would provide. Okay. There's the anatomy, there's the context. We want to do a measurement tool, and of course, you go back to the famous quotes, if you cannot measure it, you cannot improve it. So that was our motivation, is let's look at how these things are actually working in patients and see if we can make it better. Now, this is attributed to Lord Kelvin. I think it's pretty clear that he never said this. And in fact, if you cite the literature, this is what he often said, or actually said, and was documented. And I think it's just too long. They needed to soundbite it. So there you go. That's where it came from. Okay, so we wanted to measure how knees moved in a detailed way. And so an obvious choice, and many of you are familiar now with a technology called motion capture, and there's a motion capture lab on campus, right? Yes? I think? Somebody? Okay, nod. There should be. And so the idea is that you put reflective markers on the body, and you have a constellation of cameras that are suitably calibrated to where they see that marker. They can triangulate in space and know where it is in 3D, and then you map those markers to the body, and you can say where the body moved, right? And so this is commonly used by Hollywood and filmmakers for character animation and avatars and all that kind of stuff. But the technology actually grew up in clinical motion analysis, really focused on post-World War II amputees and kids with cerebral palsy. And so this is a picture of a kid that was in our lab in West Palm Beach. This is pre-HIPAA, so we didn't have to blur out his face. Probably should do that. But that gives you a sense of putting the markers on there, and we used our analysis of how he moved to help the surgeon design the treatment that would help that kid walk more naturally and have good endurance when he was walking around. The motion capture stuff also gets used very commonly in sports performance analysis. And so this is our lab in one of our motion capture labs in the orthopedic department at UF. This is a little guy named Tim Tebow, who you may be familiar with, Heisman Trophy, couple national championships, now works for ESPN. That's what he looked like as a sophomore, where we said, your throwing motion is never going to get you success in the NFL. But he did okay. So that's one way we could have gone about doing motion analysis of how knee replacements moved. And we tried, and we failed miserably. It didn't work. And the reason for that is we're trying to measure the femoral bone motion and the tibial bone motion. And if you're like me, there's some soft tissue on top of that femur, right? And so if you put those little reflective markers on the skin surface, it moves inches or centimeters, depending on which unit system you prefer. And so how are you going to get an accurate measurement of the underlying implant that's connected to the bone when what you're doing is tracking skin motion, right? Super hard. It couldn't get the precision that we needed for that measurement. And so that was a year of unproductive graduate school. Had to find another way, and we ended up developing a method called model image registration. And the idea is we still wanted to accurately measure the kinematics or motion in 3D of the implanted knee replacements. We couldn't change the implants or put little beads and stuff in the bones that would make the tracking task easier. So we didn't have the ability to do that. And we needed to do something that was dynamic. And so my research advisor, mentor, Andy Hodge, said, well, let's use fluoro. I was like, great. What's fluoro? And he said, it's X-ray video. And so here's a video of a patient with a knee replacement, and you can see the really dark black objects there. That's the metallic implants. Now, what you don't see is the plastic, which is a polymer, a carbon-based polymer. It's radiolucent. They don't show up there, but it's there. And so the idea was, hey, if we can take these dynamic X-ray images of the knee, then maybe we can figure out how to make this measurement. And so that's what we did. So the idea was that any kind of an X-ray is a perspective projection. The light starts, X-ray is just light. It's just very energetic little photons. But it emanates from a very small area, so a point source of light, and those rays diverge out, just like this projector, right? Or just like the flashlight on your phone. And so if I hold my hand here and I go towards the light source, I don't have to look. I think my shadow's getting bigger there, right? And so this is optics of perspective projection. And as I change the orientation of my hand in space, the shadow that's cast changes as well with that three-dimensional motion. And so we took advantage of that exact thing where these implants are manufactured objects, right? We know their shapes, and we can measure that projection geometry of the X-ray, and so we can simulate that on a computer. And if we can put a virtual implant in that space and then wiggle it around in the virtual space till it casts the same shadow as the patient's implant casts, then we know where that had to be in three-dimensional space, okay? And so that concept was followed by some computer coding and some Fourier transforms. You all get Fourier transforms in your math classes, right? Anybody? Yeah? Okay, I'm going to skip the next 6 slides. But basically, we figured out a way mathematically to do these measurements based on this idea that it's a perspective projection, blah, blah, blah. And it looked encouraging. We could get the level of measurement precision that we needed based on this to answer the surgeon's questions. And so the idea here, again, is we can take an X-ray image of somebody's knee, right, the black and white image. We know the geometry of that projection, where the light source is, where the screen is. We can put into that, it's just like shadow puppets. So there was math, but this is just shadow puppets. We can put in the virtual implants, wiggle them around in virtual space until they match the same projection. And then once we've got that for both of the moving objects, we can pull them out of that scene and know how they were moving relative to each other, okay? That all makes sense? So now we could measure, I could answer my surgeon colleagues' questions. Here's how the knee moves. So here's an example of that. On the left is the moving images of the X-ray. In the middle are the exact same images with those implant models superimposed and registered, and then we take those motions out of this view and resolve it to the femoral component moving relative to the tibial component. That's the money shot. That shows the surgeon the motion that's going on that they actually care about, the thing that they can adjust their surgical procedure to have an effect on how that's happening. Okay? So, all right, Scott, cool. You take an X-ray video, you do this stuff, you get a nifty animation, but is what you're doing actually representative of the patient's experience with that implant? And so we went into great detail in the mechanics and materials class today on this, in great detail, on this paper where in our lab, we, in addition to doing the mechanical and motion capture studies, we had an implant retrieval program where patients, when they got their implants, just like the organ donor program, they consented for us to retrieve their implants after they passed away. These are precious data sources. And so what we were able to do is with this patient, she had been in the lab and we had done this kinematic X-ray analysis on her in multiple activities. And so we then took those in vivo, in-life measurements and said, can we predict the wear on her implants? And then had the ability to actually check if what we saw in the lab was predictive of what that implant actually experienced in her body. And this paper shows, yeah, they matched up pretty well. So it gave us confidence that the things that we could observe in the lab were actually related and predictive of how that implant would perform in that patient. And so this goes back to the early 90s. And over the years, we've employed the same measurement principle, basically fancy shadow puppets, in foot and ankle, knee replacements, hips, shoulders, spines, and whatever this is. Anybody guess? It's not a horse. So this lower, I realize my computer's on this side, so I keep going to this side of the room. Hi. What's this? What species is that? It's a dog. It's a dog. And so it turns out that the same questions that the human orthopedics surgeons have, the veterinary orthopedic surgeons have exactly the same questions. So large breed dogs have huge problems with losing their ACLs. They're called cranial cruciate ligaments in dogs. So we were able to apply these methods also in other species. We're species neutral. We're a bunch of engineers, you know? So this method has been applied pretty broadly. And we call it model image registration, right? We've got a model, we've got an image, we bring them together in registration, that's what it is. And so where we can use this, it does involve X-ray, right? So where you can use it ethically for the treatment of people and the design of enhanced devices, okay, we're going to do that, but we're going to always follow the principle, you know, as low as reasonably possible. Anytime you use an X-ray, you try to minimize the amount that you use. All right, so we've got this measurement tool, and we began using it in the early 90s. And what we saw was absolutely different than what we expected. So what we saw, the expectation is that your knee, when you flex, the femur moves posterior, whoops. Oh, don't worry. This is just a little plastic model. The expectation is that the femur would go posterior with flexion, and you would have motion that was well-controlled, sort of back to front as you extended like that. What we actually saw when we began measuring this in patients was that when they stood up, their femur was like this. subluxed posteriorly, or the tibia was subluxed anteriorly. And when they flexed, the femur was going forward instead of backwards. So basically we had motion that looked like that. So these knees were unstable. Now, y'all realize, I told you we took out the anterior cruciate ligament, so this is kind of like a colossal duh. But the dogma at the time is, well, if you reproduce the shapes of the bones, you would expect to get natural mechanics. And through this measurement, we showed you don't. And as a result of that, patients of the day, they had implants that didn't bend very well. Well, if your femur is subluxing forward when you bend, if you have the ability to flex deeply, guess what happens? The back of your femur bone hits the top of the tibial implant. You can't bend past that. That is a hard impingement. It ain't going nowhere. And so in order to get that more natural deep flexion, the femur needs to be posterior with respect to the tibia, and then you get more natural deep flexion. That wasn't happening. Patients receiving implants in that era, again, were relatively weak. And so I know Diego said, please stay seated, but in case you want to do this experiment, you don't have to. When we perceive our knees to be unstable, and for those of you that have experienced a ligament or a meniscal injury, you may have realized that when you walk or do activities, your muscles on both sides of your leg are contracting, right? So the front of your leg is the extensors, the quadriceps. The back of your thigh is the hamstrings. Those are the ones that flex your knee. And so when you're walking around, you're walking against gravity, you want the extensors working. But naturally, we include a little bit of co-contraction where both the extensors and the flexors are contracting together. That stabilizes things and makes us more robust to disturbances, like you hit a rock or you stumble or something like that. But what happens in joints that are unstable is you adopt more of that co-contraction, so your muscles are stabilizing the joint instead of the ligaments. And so if you just like put your hands underneath your thighs and you stand up, you'll realize that your hamstrings are contracting. And so when you've got an unstable knee, that happens more. Well, if you are young with an ACL injury, you can exercise your quads a lot to overcome that. But if you are a typical total knee replacement, 64 years and older, your athletic potential is somewhat diminished. And so if you're naturally adapting this co-contraction strategy where your hamstrings are providing stability, they're fighting what your quads can do. So you are going to fatigue faster, and you're going to be functionally weaker. You can't do the big step as you might if your muscles were contracting naturally. And so that was a problem. And the final thing is, if you've got all of this uncontrolled motion, this plastic bearing is going to wear out a lot faster. And so longevity was a big issue. So that's what we found in roughly the first decade of using these methods, is things were not working the way that we wanted them to. And so we said, okay, we've got a bunch of data. Let's use this data to design something that's going to provide better stability to the knee. So we came up with a set of imperatives, right? We don't know the shapes of the design yet, but it has to do these things. It has to restore more natural anterior, posterior, front to back stability of the knee. It can't just be a hinge, right? A hinge would be stable, but it wouldn't let your knee do this motion, the internal, external rotation, point your toes in, point your toes out. That's natural, so you have to be able to do that motion. We wanted the surgeons to be able to retain the posterior cruciate ligament, but not necessarily have to rely on it in case it degraded over time. And then we really wanted the surgeons to focus on restoring the natural anatomy of the femur, because we'd seen some surgical techniques changed it enough that it really affected how far the knees could bend. So those were our design imperatives. And let's put this in the context of the implants of that day. And so what you see here are 4 tibial inserts. The bearing surface is retrieved from people from those historical sort of 1970s to 90s designs. And what you'll see here is that even though their shapes are different, they're all symmetric. That is, the medial and lateral sides are exactly the same. Now that lets you reduce inventory, so it's less expensive to deliver, but your knees are not symmetric, right? The medial part is different than the lateral part. So there's something. The other thing is, if you look at these surfaces, they're all flat in the front to back or anterior posterior direction. And so they're kind of reproducing the bone shape, but when you yank out the ligaments and the menisci that normally stabilize the joint and you put in a slippery flat surface, is it a surprise that these things are unstable, right? Hopefully not. And what you see here is the kind of damage that those older materials than we use today and the poor joint mechanics led to damage of those bearing surfaces. So that's what we wanted to address. We wanted to make a more naturally stable knee, again, going to those design imperatives. So here's what we did. We said, what is missing from this knee? Well, a big one is the anterior cruciate ligament. Now, we couldn't do an ACL reconstruction here, right? So we needed to do this with metal and plastic. And what we did is in the lateral compartment of the knee, so this is a left knee, the outside compartment of the knee, what we did is we made the articular surfaces spherical in extension. So that means it's a ball in a socket in extension, but then we made that surface on the femur go to a much smaller radius back in deeper flexion. So that has the effect of providing very strong anterior posterior stability when you're in extension, and then as you flex, that joint essentially unlocks. And so now you can roll back like you would normally, okay? And so the ACL, it stabilizes that compartment in extension, and it relaxes in flexion. So we tried to reproduce that with metal and plastic shapes. So that was a key element of our design. On the medial side, this is now the inside, we had to sort of titrate what we did because on this surface, we needed to accommodate the rotation of the knee as you're walking, but we wanted it to have a little bit of a dwell point or a deepening or a sulcus so that when you flexed, it sat in the middle while the lateral side rolled back as occurs physiologically. So that was a little bit of a titration. And then again, coming back to the material properties, in the lateral compartment, it's a spherical articulation, low contact stresses, good wear performance. The medial side, less conforming, because we needed to be able to do this, higher contact stresses. So what we did is we made that condyle wider. We gave it a bigger footprint to distribute the loads. So that's what we did. This we called the data-driven design, or the 3D knee, and we implemented it. And so the question is, well, great, Scott and Andy, you implemented it. Did it work the way you designed it to? And so, of course, having based the analysis on the fluoroscopic kinematics of lots of different designs, we did it on these two. And what we showed is that in deep flexion activities, our patients got really good flexion, the normal internal, external rotation and translations, much like what happens in the normal knee, but just not as much. Not as much rotation, not as much translation, but the same patterns of motion. And when we had people walking on a treadmill, they had extraordinarily repeatable and stable knee motions. And so this little plot, there are 500 red lines there from 500 frames of data, 13 different patients, and it is very, very consistent that shows if you put a ball and socket in there and you put a little load across it, it's a ball in a socket. You know, it's stabilizing the joint as we wished. So mechanically it was working the way that we wanted, but no patient is ever going to come into the office and say, Doc, it feels like about 5 to 10 degrees of internal external rotation and 5 millimeters of translation. You know, that's never going to happen. But what they're going to say is, it feels stable, or it feels unstable, or I get tired quickly. just doesn't feel right, or, oh, it feels good. And so we also tested these folks in the motion capture lab to look at their functional knee strength in demanding activities and using electromyography, monitoring the muscle activities, were they exhibiting excessive co-contraction? And the answer was 85% of normal strength, which is as high as has ever been published on a knee replacement, and they had natural muscle contraction patterns. They weren't adopting that co-contracting strategy that basically drains their extensor capabilities. So mechanics looks good so far. The other thing that we were concerned about was wear, right? I showed you a whole bunch of really damaged implants. We wanted to make sure that that wasn't going to be a problem. So Clemson University specializes in benchtop wear testing of implants, and they publish all the data. And so here's a bunch of different implant designs with a bunch of different material properties. Here's our knee. It's about 2 milligrams of wear per million cycles in these standardized tests. It's really, really low. And importantly, there's groups that have done analyses to suggest that in this kind of testing, if you are below 5 milligrams of wear per million cycles in that region, those are the implants that are likely to last for the lifetime of the patient. You're not going to be predisposed towards, we call it osteolysis, where the wear debris makes the bone angry and the bone resorbs and the implants loosen. We call that osteolysis. So that looks good as well. So all the mechanics seem to be well addressed. Okay, how did it work in patients? So in the early going, we just kind of worked with surgeons here and there. This design was first implanted in 2001, and it has the shiny surfaces have not changed since. Here's an analysis of 159 knees, 2 different surgeons, and in the early going at 8 years on their knee society score, so this is a rating of their pain and clinical performance and their function, they're in the 90s. So that's an A, right? At Elon, that's an A, right? Okay, so good, and their flexion performance, average 124 degrees, almost 80% of the patients had more than 120. For traditional knee designs, those averages were more like 105 degrees. And so the flexion performance was really good. Okay, give us a big head-to-head study. So here's one that came out of the University of Indiana, where we compared people that had this so-called data-driven design knee, asymmetric, different congruency, medial and lateral, versus one of the world's highest selling implants. This is used today and is one of the highest volume implants. And what you realize is it's symmetric and it looks pretty darn flat, right? Kind of like the old school designs. But they put it in with robots and have fabulous marketing, and that's what the patients get. So 183 patients with each design, very carefully matched by their clinical profiles, age, height, weight, sex, BMI, all that kind of stuff. And at a year, did all of the clinical outcome metrics, the patient-reported scores, so the patient's reporting of their experience, their physical activities, and their satisfaction. And what we found is that, as you might expect, in this asymmetric design made to restore more natural stability, they had less pain when they were walking, right? The regular symmetric design that was not controlling the motion in any intentional way had more pain while they were walking. And that was statistically significant. With the 3D knee versus the traditional one, there were significantly more of those patients that reported no pain and significantly fewer of those patients that reported severe pain. And this was not statistically significant, but twice the percentage of the 3D knee patients had high activity sports level performance compared to the traditional one. So in a large, well-controlled study, the mechanical performance of these patients was superior with this design. So yay, right? This is the last paper that I'll cite for this part. And this is going to be published in the Journal of Arthroplasty this summer. I was hoping it would come out, but it will come out shortly. And so it's a really big series of 1,300 patients with these knees. And so lots and lots of data, all comers. Every patient that received this consecutively, 1,300 cases. Again, followed up in up to 7 years out, but importantly, 260 of these cases were 5 years out. And what they saw is that the patient-reported outcome measures, the PROMs, all significantly improved. That was highly statistically significant. Greater than 86% of the patients achieved, they call it the minimum clinically important difference, so a measurable improvement in their outcome by a couple different metrics. 89% of the cases reported their knee sometimes or always felt normal, and that's the graph here. Preoperatively, 68% of the knees never felt normal, 30% of the knees sometimes felt normal, and then the balance, I guess those 2%, their knee always felt normal, and you might ask, why are you getting a knee replacement? But I don't know. But after the knee replacement, we've got this 89% of the cases always, sometimes or always felt normal, and almost 60% of the knees always felt normal, which for a knee replacement is, woo, that's awesome. And then at the folks that had gotten to 5 years, 93% reported that they were satisfied or highly satisfied. And the context there is, in most large series, the percentage of people who are satisfied or highly satisfied is somewhere between 75 to 85%. And so we're getting pretty close. 2% of these people, their knee felt normal. So you're going to have a hard time making them feel better. And we're getting 93% at 5 years that say, they're really satisfied with what's going on. So clinically, this is a success. So yay. We did measurements, we designed something, and after 20-some years of work, showed that the clinical results, the weight-bearing results, the wear results, all of that, and the satisfaction was really good and in many cases superior to the other designs on the market. So that's an engineering success. But importantly, so far about 150,000 of these have been implanted, and it's growing at 30% a year. So the word's getting out. It works. But let's bring it back. Instead of 1,000 patients, here's one patient. Her name's Cinta. She was the very first 3D knee patient. She was 46 when she received her knee. She had lupus, and it had destroyed her knee. And she was a high adventure guide that took people rafting and hiking through Big Bend National Park. That was her job. So extraordinarily active woman, outdoors, and we stayed in contact. And you can see the quotes here that at 10 years and then 13 years after her surgery, and then even recently, she's still very active, and now at 68 years old or 69 years old, continues to have that knee performing very well. And I can tell you, as the designer of that knee, meeting with people like this that have had an experience where your widget had a profound effect on their life, talk about motivation. Let me get back into the lab and let me bring in a bunch of young people to do this kind of stuff. It's extraordinarily motivating. So there's the trajectory: make a measurement, do something about it, design something, and get it into the clinic. Let's spend 1 or 2 minutes getting back to the measurement. So, a little context: people began looking at knee kinematics back in the 1830s. Anatomic studies, the Weber brothers. They published in German, so nobody read it in the English language for 100 years. Post-World War II, because we had a lot of amputees, there was a lot of work in orthotics and prosthetics and biomechanics, a real resurgence. In the 1970s, folks began using X-ray methods, static X-ray methods, to quantify skeletal stuff. And then, this is 1988 when a Mass General surgeon told an MIT student, hey, figure out how knee replacements move after I put them in. I did my dissertation as I talked to you. And for the past 30 years, our community has used these methods and variations on them and improvements on them. and published thousands and thousands of papers. This is now a standard method in biomechanics. Awesome. We have filled the literature doing this model image registration stuff. Not a single clinic on this planet has yet adopted these techniques to treat patients on a daily basis. And if you talk to surgeons, they may often tell you, well, a journal paper doesn't treat a patient, I do. And so this kind of gnawed at me, that we hadn't gotten into the clinic. So a little bit back more to the contextual. So we go back to the fall of 2022. Here's where I'm at. I'd worked in orthopedics since 1984. I'd run a hospital-based lab. I'd been an engineering faculty doing classes, research, over 200 journal publications. They'd been cited and all that kind of stuff, patents, awards, blah, blah, blah. 300,000 patients have received this implant or another one that I was involved in. I feel really good about that. Graduated students. I've hosted and worked with 40 orthopedic surgeons as trainees, so engineers and surgeons working together. And then I also had the misfortune of being in an administrative position at one of the largest departments at the University of Florida, where we have 2,000 undergraduates and 500 graduate students, and we had a pandemic. So that was a blast. But that, in sum, looks like a pretty successful academic career, right? I could just stick with that. All good. The trajectory was fine. But that fall, my youngest, so Matt's our oldest, our daughter Jenny finished graduate school in mental health counseling and got a job. I turned 60, and I got diagnosed with prostate cancer. So it was like this big wake up, like, okay, Scott, you're not going to work forever. What do you need to get done? And this measurement thing, getting it in the clinic, was work that was left undone. And so, this year, here's my snapshot. So I resigned from the University of Florida. I'm no longer a state of Florida employee. I still have my academic appointment, so I can take care of students and stuff, but I'm a volunteer there because now I can move much faster in developing intellectual property and commercializing it than I could with a multi-billion-dollar battleship of the University of Florida. And so that's the decision that I made. I am working with the company that did the 3D knee replacement to create the next version. So we've learned a couple things over the last 20 years, and we think we can make it even better. We started a company called Scientific Motion Technologies that's bringing a very funky set of shoes that can be sort of modified in a way that helps people retrain how they walk so that they actually get a lot of pain relief and can put off getting a knee replacement. Or if they have a knee replacement and it's painful and it's not working quite the way they want, we can still retrain how they fire their muscles and they get pain relief. So we're super excited about a non-surgical method to help folks with knee pain. And then this company, this is where I'm spending most of my time, it's called Orthopedic Driven Imaging. And this is the company where we want to take this research method and bring it to the clinic. So this is pictures that I took in the lab last week. We are developing novel hardware and software to bring these measurement methods in the clinic where the surgeons who have been asking for this for 30 years, they say, Scott, I want to do these kinematic measurements in the clinic. When can I have it? It's like, okay, now we're going to deliver it. And so it's a startup. We founded it last summer. I've partnered with a couple of folks that know how to do this, business people, hardware, software people. We've completed our A and B financing rounds. All of that startup stuff has been good. And we believe we'll have our MVP, our minimum viable product, in clinics this year. So it's been a very quick ramp up to bring this stuff into the hands of surgeons who are the people that we're trying to help. I mean, they help the patients. We're trying to help them help the patients. And so there you go. That's a trajectory of engineering in the medical sphere. Some lessons, some summaries. I got involved in research and in doing stuff as an undergraduate. And if you have not, the students here, if you have not already done that, please take the opportunity to at least find out what's available. I know 30% or more, Nancy, do I got that right? 30% or more of Elon students are involved in research as undergraduates, and there's no reason that couldn't be 60%, right? Let's be aspirational. But that had a profound effect on my experience. And as you saw, I was lucky enough, fortunate enough to find mentors who were passionate about their mission that they were following, and that obviously influenced my ability to grab onto a mission and then use that to direct my career. You know, my resignation from UF was not an arbitrary thing. It's the way I frame it. I'm on the same mission, it's a different vehicle, right? The mission hasn't changed, it's just the job title that's changed. So, and that's been critical for me. And then for the young folks, I would encourage you not to wait till you're 60 to really have a think about where am I on my career. Maybe do it every couple of years. You know, don't wait till you're 60. And I really appreciate you all coming out tonight, the opportunity to share this. And I'll be here for a while if you've got questions. I realize we probably have consumed our hour, but if you've got questions, I'm really thrilled to answer them. So thank you very much.